Hello, Sandberg Algebra students. This lesson is on factoring polynomials completely. This lesson basically takes everything you've learned throughout the chapter so far to the next level. And if you dig pretty good on all of the quizzes so far this unit, this should not be that hard. Basically, every factoring problem we approach now, the first thing we always have to look for is a greatest common factor. Okay, so let's go through a couple of examples, and then you can go off on your own and try some. So when I look at the first example here, every factoring problem I approach, I don't care if it has 2 terms, 3 terms, 4 terms, 5 terms, I don't care how many terms it has. The first step is to look at every term and ask yourself, can I factor out a greatest common factor? So here we look. We have 4 terms. Generally, 4 terms clues us in on grouping, but before we can even do that, first thing I want to do is look for the greatest common factor. So when I look 12, 8, 30, and 20, what is the largest number that goes into each of those? And that would be 2. Okay, now n to the third, n squared, n, and 20. Does every term have an n? No. So right now the greatest common factor is just 2. And if I go ahead and divide each of these terms by 2, I'm left with 6n to the third minus 4n squared plus 15n minus 10. Now what you have to see here is we have this remaining polynomial. Before we can stop, we have to ask ourselves, can this be factored? And when I look at the remaining polynomial, I like to copy and paste it on the side. Once I do that, I identify what factoring method I have to use. Since there are 2 or 4 terms in here, I know the grouping method would probably be the best one to use. So I group the first 2 terms, second 2 terms. Now I look for a GCF here. That would be 2n squared. Okay, when I divide each term by that, I get 3n minus 2. Now here, when I look at these 2 terms, what would the GCF here be? Well, the largest number that goes into 15 and 10 is positive 5. And then only one of the terms has an n, so I cannot factor that out. So I look at the remaining polynomial. When I divide by 5, 15 divided by 5 is 3n, minus 10 divided by 5 is 2. Now, do these binomials match up? Yes. So we pull that binomial out. And what do I have left over here? 2n squared plus, what do I pull out here? The 5. Now, what you have to understand is this 6n to the third minus 4n squared plus 15n minus 10, that can be replaced with its factored form here. So you go back, you bring down your GCF from the original problem of 2, and then you put the factored form in the place of 6n to the third minus 4n squared plus 15n minus 10. So you have 2n squared plus 5. So this expression, all right, is factored, and this is equivalent to the original polynomial. Okay, it's the same thing, just written a different way. Now the second example. What's my first step all the time? It is to look for a greatest common factor. So 14 and 8 was the largest number that goes into those 2 terms. Well, 2, and does each term have an n? Yes. So I have to factor out the lowest exponent, which is n. So my GCF is 2n. Now when I divide each of these terms by 2n, 14n squared divided by 2n is 7. 8n divided by 2n is, 7n. Plus 8n divided by 2n is 4. Now, when you look at this remaining polynomial, can that be factored? Can 7n plus 4 be factored? Well, you only have 2 terms there. Okay? And you already factored out the greatest common factor. It's not a difference of 2 squares. That cannot be factored any further, so your final answer is just 2n times 7n plus 4. And you are done. Okay? So, will the remaining polynomial always be factorable? The answer to that is no. Okay, the answer is sometimes. So, example 3. start with GCF always. So 3, 24, 21. Greatest common factor is 3. Does every term in this polynomial have an x? Yes. The smallest exponent is x to the first, so we factor out a 3x. Divide each term by 3x. And when I do that, I have x squared minus 8x plus 7 left over. So I look at this remaining polynomial. Can that be factored? Well, if I pull that out to the side, this is an easy AC problem, some teachers call it, or it's a quadratic trinomial where the leading coefficient is equal to 1. And to factor this, all you have to do is find the numbers that multiply to give you positive 7 and add up to give you negative 8. Well, you have to multiply to get a positive and add up to negative, so both of your signs would be negative. Negative 7, negative 1, negative 7 minus 1. We're happy in both. Therefore, the factors that add up or multiply to give you 7 and add up to negative 8 would be x minus 7, x minus 1. Are we done? No. We have to take this factored form and substitute it back in. So our final answer would be 3x times x minus 7 times x minus 1. And we are done. Okay? This is no different than what you've been doing the entire unit. Next one. I look at 10x squared, 6x, and 28 and look for the greatest common factor. That greatest common factor is going to be 2. Okay, so I factor out 2. Does every term have an x? No. So when I factor out the 2, I divide each term by 2, and I end up with 5x squared plus 3x minus 14. Now, you have this remaining polynomial. You must look to see if it is factorable. Will it always be factorable? No. But a lot of times it will. So, we have 5x squared plus 3x minus 14. What method would I have to use here? I would have to use the AC method. So, what numbers multiply to give you AC, which is 5 times 14? Okay, what is 5 times 14? It is 70, or sorry, negative 70, because it's negative 14. And then adds up to that middle term, which is 3. Well, that ends up being, sorry, there's no room here. Numbers that multiply to give you negative 70 add up to 3 would be 10 times negative 7. Okay, so what do? We use these factors to split that middle term. So we bring down the 5x squared, then we split this middle term and write plus 10x minus 7x, because remember that would give us 3x, and then we bring down that minus 14. Once we split that middle term, our next step is to group. Remember that's negative 7x. So greatest common factor here would be 5x. So we have 5x times x plus 2. And here, because this was negative 7x, we have to factor out a negative, and then the common factor between 7 and 14 is 7. And what do I have left when I divide these by negative 7? I have x plus 2 left over. Do my binomial factors match up? Yes. X plus 2 times 5x minus 7. Now, again, I'm not done because I have to rewrite it with the factored form of the remaining polynomial and the original GCF. So, final answer, 2 times x plus 2 times 5x minus 7. If you were to multiply these out, you would get the polynomial you started with. Number 5. Generally, anytime I have two terms, I have one term here and one term here, linked by subtraction. Generally, I know I have a difference of 2 squares. But right away, do you notice? Well, you should notice that 27 is not a perfect square and 125 is not a perfect square. So what do we have to start out for? The GCF. What is the greatest common factor between 27 and 125? Well, you should notice that 3 goes into both of them evenly, So greatest common factor here is 3. So when I divide each term by 3, I end up with 9x squared minus 25y squared. So looking at this inside polynomial, is that polynomial factorable? Well, is 9 a perfect square? Yes. Is x squared a perfect square? Yes. Is 25? Yes. Is y squared? Yes. Are these linked by subtraction? Yes. This is a difference of two squares. So square root of 9x squared is going to be 3x. Square root of 25y squared is going to be 5y. So we know this will factor out to be 3 times 3x plus 5y times 3x minus 5y. Remember, on a difference of two squares, you basically take the square root of each term, you add them, and you subtract them. But don't forget you had a GCF at the very beginning that you have to bring down to your final answer. And that's it for that one. Number 6. Is there a GCF in this problem? No. But you have two terms, both linked by subtraction. Can you take the square root of x to the fourth? Yes. Can you take the square root of 81? Yes. This ends up being a difference of two squares. So when I take the square root of x to the fourth, remember, it's going to be x squared. You divide the exponent by 2. Square root of 81 is 9. So when I factor this, since it's a difference of two squares, once I find the square roots, I basically add the square roots and I subtract the square roots. Now it looks like the problem's done. There's no GCF, I factored it, but when you look at the first binomial factor, x squared plus 9, that's not a difference of two squares. But when you look at the second binomial factor, right, x squared minus 9, is x squared a perfect square? Yes. Remember, how do I know that? The exponent of the variable is even, you know it's a perfect square. Okay, is 9 a perfect square? Yes. That second binomial factor can be factored again. So I keep the first binomial factor, but the second one, square root of x squared is x, square root of 9 is 3. Remember, to factor this remaining polynomial, I would do x plus 3 times x minus 3. So anytime you have a difference of two squares, or basically any factoring problem, you should look to make sure there's no GCF that can still be factored out, along with make sure the remaining polynomial, is not factorable. Okay, because you are not completely finished until everything is factored completely. Hope everything makes sense here. Feel free to watch a certain problem again and do the remaining problems on the back side of the worksheet. Have a good day.